Hi, this is Andrea Hendricks. The topic of this video is on verifying trigonometric identities. We've already done some of this work, but we'll just review some things first. First of all, what is an identity? An identity is an equation in which both sides are equal for all values of the variable. Our goal is to work with one side of the equation and make equivalent replacements using the fundamental trigonometric identities until the other side is obtained. So the only problems that you need to worry about from this section in the textbook are these problems that I have listed here, which is also in your syllabus. I've worked through a selection of these problems to give you the feel for how these will be done. So if you have any questions, please don't hesitate to contact me. So let's begin with number 2. It is secant y times cosecant y is equal to 1. Well, to work with that identity, we want to start with the more difficult side and work until we can get the right side. So what do we know? We know that secant y is the same as 1 over cosine y. So 1 over cosine y times cosine y is simply 1 because the cosine y's divide out. So our proof is done. Number 6 is cosine squared beta minus sine squared beta is equal to 2 cosine squared beta minus 1. Well, if you're looking at these sides, either side is about as difficult as the other, so it really would not matter which side you worked with here. I've elected to work with the left. If we start with cosine squared beta minus sine squared beta, and notice the right side is all in terms of cosine squared, so we want to try to remove the sine squared and put in a cosine squared. Well, one of the Pythagorean identities allows us to do that. We know that cosine squared x plus sine squared x is 1. So sine squared x is 1 minus cosine squared x. So in place of sine squared beta, we're going to replace that with 1 minus cosine squared beta. And now we can distribute the negative outside that parentheses to have cosine squared beta minus 1 plus cosine squared beta. Now we have like terms, so cosine squared beta plus cosine squared beta is 2 cosine squared beta minus 1. And notice that we have obtained the right side, so we are done. Number 7 is tan squared theta plus 6 is equal to secant squared theta plus 5. Again, either side is about as difficult as the other. I've elected to start with the right side here, so if we start with secant squared theta plus 5, we want to rewrite secant in terms of tangent. But again, one of the fundamental Pythagorean identities is 1 plus tangent squared is equal to secant squared. So in place of secant squared theta, we can put 1 plus tan squared theta. And then the 1 plus 5 combines to be 6. Combines to be 6, so we are done because we have obtained the other side. Now, the next set of problems is still to do the verification. They get a little bit trickier, but we can still work through this and find the result that we need. Number 21 in particular, sine to the 1/2 x times cosine x minus sine to the 5/2 x cosine x is equal to cosine x cubed times the square root of sine x. Now understand, square root of sine x is the same thing as sine x to the 1/2, and we write that also as sine of 1/2 x. Okay. So we start with the left side since it seems to be the most complicated, and we want to factor out a common factor. Notice that we have a sine to the 1/2 x, a sine to the 5/2 x. If you remember, with exponents is always the smallest power that's common, so we can take out a sine to the 1/2 x. And then we also have a cosine x in each term, so that is a common factor as well. Now to the side, you'll notice how I've rewritten sine to the 5/2 just so you can see what will happen when you take out a 1/2 power. Sine to the 5/2 x is the same thing as sine to the 1/2 x times sine to the 4/2 x. So another way to think about sine to the 5/2 x is sine to the 1/2 x times sine squared x. So when we factor out a sine to the 1/2 x cosine x from each term, notice for the original term, that's exactly what we're factoring out. So you divide it by itself and you get 1. When we take a sine to the 1/2 x times cosine x out of the second term, well, it leaves a sine to the 4/2 x, which is sine squared x. So now we know that 1 minus sine squared x is cosine squared x. So what we have is our greatest common factor, which is sine to the 1/2 x times cosine x, times what remained, which was cosine squared x. Well, cosine x times cosine squared x is cosine cubed x. And I've already talked about this, that sine to the 1/2 x is the same thing as the square root of sine x. So we actually have shown exactly what we needed to, that the left side is equal to the right. Number 26 is 1 plus sine y times 1 plus sine of negative y is equal to cosine squared y. So the most complicated side, or the more complicated side, is the left side. The thing that we're going to use here is the fact that sine y is an odd function. That tells us that sine of negative y is the same thing as negative sine y. If that happened to have been cosine, cosine is even, so cosine of negative y is the same thing as cosine y. But knowing that sine is odd, we can replace the sine of negative y with negative sine y, and then we multiply. So again, these are conjugates, 1 plus sine y times 1 minus sine y. We can FOIL them out if you wish, but what happens is that we get the difference of two squares, which is 1 minus sine squared y. And that's back to one of our fundamental identities, which is cosine squared y. Number 30, tan x plus tan y over 1 minus tan x tan y. We've got to see that that's equal to cotangent x plus cotangent y over cotangent x cotangent y minus 1. Here again, the left side and right side are equally as complicated, so we can start with either side. I've started with the left side. So rewriting tangent in terms of cotangent, tangent x is 1 over cotangent x. Tangent y is 1 over cotangent y. Likewise, we make that replacement in the denominator for tan x and tan y. And then we want to rewrite this complex fraction. To rewrite a complex fraction, we can multiply by the least common denominator of all the fractions involved. So that would be the least common denominator of those fractions is cotangent x times cotangent y. So we have to multiply the numerator and denominator by that LCD, which really means you multiply every term in the complex fraction by that LCD. So if we distribute cotangent x, cotangent y to each term in the fraction, notice that multiplying the LCD by 1 over cotangent x, the cotangent x will divide out, leaving us with just cotangent y. If we distribute cotangent x, cotangent y to 1 over cotangent y, the cotangent y's divide out, leaving us with just cotangent x. In the denominator, cotangent x, cotangent y times 1 is just itself, and then cotangent x, cotangent y times the 1 over cotangent x, cotangent y just leaves a minus 1. And that is exactly what we needed to show. Now, plugging along, number 36 is to show that secant squared y minus cotangent squared of pi over 2 minus y is equal to 1. So working with the more difficult side, the first thing you want to do is get rid of any of the cofunction, or use the cofunction identities to get rid of any of the pi over 2 minus y's. In other words, get all the angles in terms of just y. Well, one of the cofunction identities is that cotangent of pi over 2 minus y is equal to tangent y. So if we square each side, we know that cotangent squared of pi over 2 minus y is equal to tangent squared y. So we want to make that replacement first. So this left side is equivalent to secant squared y minus tangent squared y. But what do we know? We know that 1 plus tangent squared y is equal to secant squared y. So what we have here is that, well, it's right here in front of us, isn't it? 1 is really the same thing as secant squared y minus tangent squared y. And that's what we have. Secant squared y minus tangent squared y is just 1. Now we're going to verify more identities. Again, all of these you could use your graphic calculator to check, but quite honestly, I think sometimes plugging into the calculator leaves more room for error than doing it algebraically. But you can certainly do that if you feel comfortable plugging into the calculator. So number 40 is cosecant x times cosecant x minus sine x plus sine x minus cosine x over sine x plus cotangent x is equal to cosecant squared x. Okay, so we want to start with the left side, and the first thing you want to do is distribute to clear the parentheses. So cosecant x times cosecant x is cosecant squared x. Distributing cosecant x to sine x, we get the product of minus cosecant x times sine x. And then when you have a numerator divided by a single term, you can divide that denominator into each of those terms of the numerator. So that would leave us with sine x over sine x minus cosine x over sine x, plus, don't forget that, cotangent x. So a lot's going to reduce out. We have cosecant squared x. Cosecant x times sine x is really 1, right? Because that's the reciprocal, so we just get 1 for that. Sine x over sine x is 1. Cosine x over sine x is cotangent x, so we have a minus cotangent x plus cotangent x. So we get a lot of things canceling out, because you have a minus 1 plus 1, and the cotangents cancel out, which just leaves us with cosecant x. Now we have sine x in number 44 times 1 minus 2 cosine squared x plus cosine to the 4th x is equal to sine to the 5th x. So we want to factor what we have here, 1 minus 2 cosine squared x plus cosine to the 4th x. Well, that is a perfect square trinomial that factors as 1 minus cosine squared x times 1 minus cosine squared x. So we want to start with the left side. We know that 1 minus cosine squared x is sine squared x, so we make that replacement twice. So we're left with sine x times sine squared x times sine squared x. When we multiply like bases, we add the exponents to get sine to the 5th x, so we are done. Now a blast from the past, number 50 brings into play the sum of cubes. So we have sine cubed beta plus cosine cubed beta over sine beta plus cosine beta. We've got to show that's equal to 1 minus sine beta times cosine beta. Well, we start with the left side and rewrite it using factoring. The sum of two cubes, I've written this pattern to remind you, a cubed plus b cubed is a plus b times a squared minus ab plus b squared. So our a plus b is what you cube to get the original terms, which is sine beta plus cosine beta. Now applying this rule to get the trinomial, we have to square sine beta, which is sine squared beta, minus the product sine beta times cosine beta, which is here, plus the square of the cosine, which is cosine squared beta. The denominator stays the same. So sine beta plus cosine beta very neatly cancels out. So we're left with this trinomial of sine squared beta minus sine beta times cosine beta plus cosine squared beta. Back to our fundamental Pythagorean identity, sine squared plus cosine squared is 1. So we have shown that that expression is equal to 1 minus sine beta cosine beta. Now, in the next set of problems, we want to use the cofunction identities to evaluate the expression without using a calculator. So we're looking at sine squared of 35 degrees plus sine squared of 55 degrees. Well, how do 55 and 35 relate? Well, they are 90 minus the other, right? So we know that sine squared of 55 is really the same thing as cosine squared of 90 minus 55, right? Because sine u is equal to cosine of 90 minus u. And likewise, if we square both sides, sine squared u is equal to cosine squared of 90 minus u. Well, what do we know about sine squared plus cosine squared of any angle? It is 1, so that result is just 1. And then the last thing I want to show you is number 64 here. It is to show secant to the fourth x tan squared x is equal to tan squared x plus tangent to the fourth x times secant squared x. So the more complicated side is, in my mind, the right side. So we look at tan squared x plus tan to the fourth x. We can factor that, taking out a tan squared x. So a tangent squared x out of itself leaves a 1. Tan squared x out of tan to the fourth x leaves a tan squared x. Well, very nicely, 1 plus tangent squared x is one of our Pythagorean identities. It is equal to secant squared x. Excuse me. So in place of 1 plus tan squared x, we're going to put secant squared x. So now we have the product of tan squared x times secant squared x times secant squared x, which is tan squared times secant to the fourth, which is exactly what we needed to show. Okay, so this is really just more of the same. So try to work on these, get comfortable working with the identities and making the replacements, so that fundamental identity chart will probably be seared in your brain forever after doing these problems. But they're fun. If you like solving a puzzle, think of it like that. So please don't hesitate to contact me if you have any questions on these topics.